Hello, welcome to this video. Today we're going to evaluate this integral. So we know the integral from 0 to infinity of sine x over x dx is pi over 2. But if we add on this factor of sine x over 3 divided by x over 3, and then times sine x over x, and we integrate from 0 to infinity, what is that going to be? So that's what we're going to do today, and as a tool, we're gonna prove this first. You can go from 0 to infinity of cosine x e to the negative sx is s over s squared plus 1. So let's see. Well, and I'm gonna do it like this. I'm gonna use imaginary numbers. It's not needed to use imaginary numbers. I just think it's a bit maybe nicer and gets the solution a bit faster. So this is the real part of the little to infinity of cosine x e to the negative sx dx plus I times the coefficient to infinity. Now let's think. We want something with cosine plus I times something to be like something with an exponent of e that we can easily integrate. Well, that will mean we'll use the Euler's formula, which says e to the ix is cosine x plus I sine x. So what we want to put here is sine x e to the negative sx dx. So when we'll combine these two, cosine x plus I sine x will turn into e to the ix. And then this is the real part of the integral from 0 to infinity. Now, like we said, this is going to be e to the ix times e to the negative sx dx, which is going to be the real part of the integral from 0 to infinity of e to the I minus s x dx. Now e to some constant, the x. If we integrate that, it's going to be the same thing but divided by this constant. This is going to be the real part of, we'll have e to the I minus s x divided by I minus s, going from 0 to infinity. Now at x equals infinity, this thing, well, we'll have e to the ix, which you can see is cosine x plus I times x, plus I times sine x, which is always bounded, and it's times e to the negative sx, and I also forgot to mention we need s bigger than 0, otherwise you can see the integral just won't converge. But if s is equal to 0, indeed, e to the negative sx will go to 0. So we'll have, maybe I'll write that down. We'll have e to the ix times e to the negative sx. This will be always bounded because cosine and sine are bounded. This will tend to 0, meaning that in total, this thing will tend to 0. And 0 divided by this constant is 0. So at x goes to infinity, this thing goes 0. So we just need to plug in 0 and take the real part of that and add a minus sign. Because we're doing it at infinity, minus at 0, and infinity it's 0. So we get the negative of when we're evaluating it at 0. So x equals 0 means this will just be 1. This is negative 1 over I minus s. This is the real part of 1 over s minus I. I'm going to multiply and divide by s plus I, and then we'll have s minus I times s plus I, which we know is s squared minus I squared, and I squared is negative 1, so this is s squared plus 1, which importantly is a real number. Because I also forgot to mention that s needs to be a real number. I mean, if it's positive, it has to be a real number. Yes. So this is going to be the real part of s plus I divided by s squared plus 1. Now this is an imaginary number. It's s over s squared plus 1 plus I times 1 over s squared plus 1, meaning that the real part of it is just s over s squared plus 1. And my challenge to you is evaluate this integral, show it's s over s squared plus 1, but using a different method that does not involve imaginary numbers. This just to me is maybe a little bit cleaner and shorter, but nonetheless, we've proved this. Now let's jump into this. Okay, so we want now to evaluate this, and the real trick here is gonna be using Feynman's trick, or maybe do a Laplace form, whatever you want to call it. But essentially, the trick is looking at the function it, which is the integral from 0 to infinity of this thing, sine x over x times sine x over 3 or x over 3 times e to the negative x t dx. This is called the Laplace form of this function. I'm going to be referring to it as Feynman's trick. So what we really want to do is to get rid of these x's at the bottom. If we can somehow do that, then we're good. And the trick involves differentiating this I to get an integral that's maybe nicer to work with, evaluate it in terms of t, and then integrating back to get a solution for this. So here's what we're going to do. We're going to start differentiating I prime t. Let's see where it leads us. So this is going to be the integral. It's the derivative of the integral here. So that's the integral of the derivative. And then this is a constant in the t world. And this is not a constant in the t world, but its derivative is negative x times it by the law of by the chain rule. Meaning that this is going to be sine x over x. And I'm just going to already put the 3 outside here times sine x over 3 divided by x times negative x times e to the negative xt dt. Now notice, one of these x's canceled out. And I'm going to write what's left. So now it's just the product of these signs divided by x times e to the negative xt dt. And we almost got rid of it. If we get rid of this other x somehow, then we might be able to transfer it into an integral that might be easy to work with in some sense. And you can see here, we got rid of one x by differentiating and getting this extra x. What if we do it again? Let's differentiate again to get the second derivative of I with respect to t. This time I won't exactly write all the details, I'll just say it. I will have negative x, we'll have the integral of this thing times negative x. X will cancel out, and the negatives will cancel out. And in the end, we'll have 3 times the integral from 0 to infinity. Sine x times sine x over 3 e to the negative xt dx. And these integrals should be dx, not dt. Okay? And now there is, but now we've reached this point, and it seems a little hard to know what to do next, because we have the product of signs. But the product of two signs can be easily expressed by half the sine of two cosines, like so. Um, let me write it here. So sine alpha sine beta, or I should say rather half of the difference, is half cosine alpha minus beta minus cosine alpha plus beta. So in our case, alpha is x over 3, and beta is x, alpha is x, and beta is x over 3. So I'll have 3 times. Now I'll already take this half out, so I'll have 3 over 2. Then they go from 0 to infinity. X minus x over 3 is 2x over 3. This is cosine 2x over 3 times e to the negative xt dt. Then minus, I'll already separate the integrals. 3 over 2 times the integral from 0 to infinity. Here we'll have cosine of x plus x over 3. That's cosine 4x over 3 times e to the negative xt dx. Again, I should write here dx, not dt. And now, I'm going to be doing a u substitution to both of these integrals to get to an integral of this form. So let's do here, u is 2x over 3, so dx is 3 over 2 du, and here the v will be 4x over 3, and dx will be 3 over 4 dv. And here, what we're going to have is this. 3 over 2 times 3 over 2 is 9 over 4. And the integral from 0 to infinity, because u at x equals 0, u is 0, x goes to infinity, u goes to infinity, so the bounds stay the same. We'll have cosine u times e to the negative. Now let's see, x is 3 over 2u, so this is going to be 3 over 2t times x dx, and then minus, this time I'll have 3 over 4 times 3 over 2. That's 9 over 8 times the integral from 0 to infinity. Okay, 4x over 3 is v, so this is cosine v times e to the negative what? Well, x is 3 over 4v, so this will be 3 over 4t times v. I should write here u, not x. And it should be here du. And yes, it should be here du, and this should be here dv. Okay. Seems right. Now, let's use this, because we in here our s is 3 over 2t. Here our s is 3 over 4t. So we'll have something like this. We'll have 9 over 4 times, that's going to be 3 over 2t divided by 9 over 4t squared plus 1 minus 9 over 8 times 9 over 8 times 3 over 4t divided by 9 over 16t squared minus 1. Okay. Now, let's see. This is going to be, after simplification, I believe it's going to be 3 over 4 times 18t divided by 9t squared plus 4, should be plus. Yes. And then here we're going to have the same thing. 3 over 4 times 18t divided by 9t squared plus 16. C. So let's clear the board, find I prime t, then find it, and finish the problem off. Alright, let's evaluate I prime t. It's going to be the integral of I double prime t. So it's going to be integral of this minus 18t divided by 9t squared plus 4, then minus 3 over 4 times the integral 18t divided by 9t squared plus 16. Now this, if you do a quick use substitution, this it will turn out as natural log of 9t squared plus 4. And this will be natural log 9t squared plus 16. So by log rules, we'll in total have 9t squared plus 4 divided by 9t squared plus 16. Because as a reminder, natural log A minus natural log B is natural log A over B. So in our case, this is the A, this is the B. We could combine those. And we have a plus C, which is a bit irritating. But no worries, we can get rid of it. Because we secretly, well, the way to find this value C is to know a value of I prime t. But I prime t, let me remind you, is this thing. And it seems a bit monstrous, and like, how can we possibly know a value of the function, this integral? But we don't really know a value of the function, we know a limit, because you can see, if we do the limit as t goes to infinity of I prime t, this thing will tend to 0, so this thing will tend to 0, so the entire thing will tend to 0. So the limit will be 0. So if we take the limit here, I'll have c plus, the limit is t goes to infinity, 3 over 4 natural log 9t squared plus 4 divided by 9t squared plus 16. We know this is 0, but we can, to evaluate this, we can do something like this. So c plus, I'm going to take the 3 over 4 out, and the limit of a natural log, I'll be able to say the natural log of the limit. Limit is t goes to infinity. 9t squared plus 4 divided by 9t squared plus 16. Notice this, because t squared are the highest powers, the 9t squared are the dominant parts. So this will be like 9t squared divided by 9t squared, which is 1. So if this limit is 1, natural log of 1 is 0, this entire thing goes to 0. So c plus 0 is 0, that means c is 0, and so in our integral we can just ignore it. Something like this. So I prime t is just this thing. Now we want to find I of t, and we don't really want to find I of t, we want to find I of 0. As a t equals 0, let me remind you, the I of t is just the integral of this times e to the negative xt. So at t equals 0, e to the negative xt is 1, and we will indeed find our integral. So this is I of 0, and by a similar thing that we had going on here, the limit as t goes to infinity of it is also 0. I'll let you check that alone. So this will be the negative of, the limit as t goes to infinity, it minus I0. And this is exactly negative the integral from 0 to infinity I prime t dt. And now we need to just evaluate this, and we're done. So this is negative the integral from 0 to infinity. Well, I'll take out the 3 over 4, natural log 9t squared plus 4 divided by 9t squared plus 16 dt. Now, I'll put the negative inside and I'll flip that around by logarithm rules. So I'll have 3 over 4. And again, by logarithm rules, I'll be able to separate it like so. So we'll have the natural log of 9t squared plus 16 dt minus 3 over 4, the integral to 0 to infinity, natural log 9t squared plus 4 dt. Now, I'm gonna use integration by parts. So here I'll have I'll use u as natural log 90 squared plus 16, and dv will be dt. So v will be t, d will be 18t divided by 90 squared plus 16. And similarly, I'll use a similar u substitution here. U tilde will be natural log 90 squared plus 4. dv tilde will be dt. So v tilde is t. And du tilde is 18t divided by 90 squared plus 4. So this integral will be as follows. This is the integral u dv. This is u times v minus the integral v du. 3 times 4, I'll just take it out. And we'll have t natural log 90 squared plus 16. And this all goes from 0 to infinity. And then minus, I'll change the order a bit. We'll have t natural log 9t squared plus 4. So t goes from 0 to infinity. So as you might suggest or see, we'll be able to combine those by logarithm rules to this thing, and then ignore this because this just says the same thing as what we're subtracting, as that minus that is the same as net. By logarithm rules, we're able to combine those and make it like so. Now we have left minus the integral. V du will be, this is from 0 to infinity, 18t squared divided by 90 squared plus 16 dt, and then plus, because here would have minus the integral, so that's plus the integral from 0 to infinity of v tilde du tilde. That will be 18t squared divided by 9t squared plus 4 dt. Close this. Now, I won't show what this is. At t equals 0, this is obviously 0. At t goes to infinity, and let you check alone that by using L'Hopital's rule, this thing will also tend to 0. So this entire thing is 0. That's maybe homework. And the rest will be like so. Have 3 over 4. Now we'll combine those into one integral. Okay, we have this. Now, I'm comfortable with working with 1 over some quadratic expression. I don't like it that there's a t squared on here. So what I'll do is add and subtract 2 in order for this to be some constant rather than a constant times t squared. So I'll use this, so I'll do this minus 2 minus this plus 2. So the minus 2 and the plus 2 we'll use them both to get rid of these t squareds. And I'm gonna let you check quickly that what we have left is we'll have 32 divided by 9t squared plus 16 minus 8 divided by 9t squared plus 4 dt. Now, this is gonna work like this. I'm gonna separate the integrals again and move the constants out. 32 times 4 is 8. This is gonna be 24. As the integral from 0 to infinity, 1 over. I'm gonna take out a 16 and write 3t over 4 squared plus 1 dt. And then 8 times 3 over 4 is 6, so I'll have minus 6, and it'll go from 0 to infinity. Again, I'll take out a 4 this time, and I'll have 3t over 2 squared plus 1 dt. Now, I'm going to have okay, 24 divided by 16, after canceling out 8, will be 3 over 2. And so 3 over 2, that's 2 times 3 over 4. This is going to be 2 times the integral from 0 to infinity. 3 over 4 divided by 3 over 4t squared plus 1 dt. And then here, we're going to have 6 over 4, which is 3 over 2. So I'm going to already put the inside. So this is the integral from 0 to infinity. 3 over 2 divided by 3 over 2t squared plus 1 dt. And I'm doing a use substitution. This will be exactly like the integral of 1 over x squared plus 1. And this will also be the integral of 1 over x squared plus 1. So this will, at the end, maybe I'll use w to not confuse it with this x, but it doesn't really matter. It's going to be 2 times an integral minus the same integral. It's going to be just one copy of that integral. W squared plus 1 dw. Now this, we know the integral of this. It's the arctangent of u. So here we'll have arctangent u going from 0 to infinity. At u equals 0, arctangent is 0. At u goes to infinity, arctangent approaches pi over 2. So this gives us a final answer of pi over 2. So this integral is pi over 2, and this integral, even after we added this factor, sine x over 3 divided by x over 3, still stayed pi over 2. And that gives us the final solution. And finally, that's it. And if you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.